So you can probably see that chemists are more concerned about the heat Q in a reaction than they are the work W. In physics, you will definitely use heat and work for different kind of calculations, jazz like that. But in the chemistry world, heat is important. Now, if the heat is transferred, exo or endothermic, but if it's transferred at constant pressure, which gets the symbol Q sub P, then Q sub P, heat transferred at constant pressure, gets a special name, enthalpy. And enthalpy is delta H. And we're going to talk about enthalpy quite a bit in this class as well as in Chem 223. Earlier we saw how the overall energy of the universe equals heat plus work. You don't create or destroy any energy, and heat and work are about that. If the heat is being transferred at constant pressure, then delta E equals delta H enthalpy plus the work. But most of the time in chemistry, the work is almost zero. There's a few exceptions when it's not, but boy, by default, it's going to be equal to zero. So most of the time, that enthalpy equals the overall energy change for a reaction. So if you can calculate the energy change, the enthalpy for a reaction, you've got the overall energy change, which is pretty cool. Delta H is just like Q. If delta H is a positive number greater than zero, it's endothermic, so energy is needed to make that reaction happen. On the other hand, if delta H is a negative number less than zero, that means it's exothermic and energy is being released by the system. There are lots of different delta H's. We're going to talk about delta H VAP, delta H reaction, delta HF, and there's lots of different things. Those are all specific delta H's for a specific reason, and we'll talk about them as we need to. But all those delta H's are just enthalpy, and enthalpy is really important because most of the time, the enthalpy change of a reaction is equal to the energy change for the overall reaction, and that's kind of cool for chemists and people that study thermodynamics. This reaction is the combustion of propane. Propane is C3H8. Combustion reactions are something organic usually, plus oxygen, making CO2 and water. Notice it says that the standard molar enthalpy of combustion is minus 2044 kilojoules. And it says, is this reaction exo, endo, what need more information, et cetera, et cetera. Well, big surprise, punchline, that's a negative number, and that's an enthalpy. So if enthalpy is negative, that means that it's going to be exothermic, all right? You literally just look for the sign of delta H to see if it's exo or endo. Negative means exothermic. Positive means endothermic, so no problem. So delta H reaction is probably the most common of the delta H forms, and it's the enthalpy change for a reaction to take place. So in the lower right-hand corner there, that's hydrogen and oxygen making water. The delta H for that reaction is minus 484 kilojoules. So to make that reaction go with 2 moles of H2 and 1 mole of oxygen making 2 moles of water, you're going to get energy out. It's exothermic. You're going to get 484 kilojoules out. And by the way, a kilojoule is 1,000 joules, or 10 to the third joules is 1 kilojoule. Don't let that interrupt you or confuse you. Sometimes you'll see reactions like in the lower left right there. This is another way to write those kind of reactions. And notice that the reactants are on the top and the products are on the bottom. When you go top to bottom, those are the exothermic values. So that's another way to show exothermic. That's more of a physical chemistry kind of application of these, but if you do see it, I just want you to know. If the arrow would have been going up, that would have been endothermic. We're going to try and keep it more like the reaction there on the right. That's a true thermochemical equation. Delta H values, delta H reaction values, depend on how the reaction is written, and it also depends on the phases of your reactants and products. So let's look at this reaction, which is hydrogen gas and half of an oxygen molecule making water. And again, I don't usually like using fractions, but I'll tell you there's going to be something coming up that I have to use fractions too. Either way, this delta H is minus 242 kilojoules, so it's exothermic. And you can think about that as making 1 mole of gaseous water, you're going to get minus 242 kilojoules of energy out. However, let's say that your instructor said, you better get rid of that fraction. So you multiply everything through by 2, no problem. You can take that old delta H1, which was minus 242, and just literally multiply it by 2 to get the new delta H. So delta H for that second reaction will be twice the first one. It's going to be minus 484 kilojoules. So if you multiply a reaction by 3, you'll multiply the delta H by 3, etc., etc. But then, oops, I forgot, we're actually not making water, we're breaking water down. So we want to have water as a reactant making hydrogen and half of an oxygen. So compare this to the first one, to delta H1. The reaction is basically the opposite. We flipped reactants and products around to get this new version in green right there. So delta H3, the value of it is going to be the opposite sign of delta H1, because in delta H1 we had reactants going to products and water was being formed. In delta H3, the water gas is breaking down to H2 and 1/2 O2. So this, if you flip a reaction, you just change the sign. What was endothermic becomes exothermic. What was exothermic becomes endothermic, etc., etc. Finally, all of these reactions have used gases: H2 gas, O2 gas, water gas. Maybe you want to have a good glass of water, liquid water, no problem. But your delta H value will be different. So when you make H2 and oxygen, add oxygen to it to make liquid water, your delta H has a different value than in gaseous water was made. This particular one is minus 286 kilojoules, a little bit more exothermic than when you're just making gaseous water. These thermochemical equations are just regular chemical equations, but they have the energy part associated with it. And there are different ways to write the energy component. So what we'll do most of the time is what you're seeing in the top right there. This is methane and oxygen making CO2 and water, and the delta H value minus 802 kilojoules. However, sometimes it will be helpful to think about that minus 802 number. That's energy being released by the chemicals. So that means 802 is going to be like a product. It's something that the methane and the oxygen are releasing. So if you see 802 kilojoules as a product, that's an exothermic reaction. It's an alternate way to write how much energy is being released. On the other hand, of course, if the 802 was a reactant, then it would be a positive delta H. You need that energy to make the reaction go. So either way is fine. You can use them. Most of the time we'll use delta H equals and then negative or positive. But if you see energy as a product, that's exothermic. And likewise, energy as a reactant would be endothermic. If you think about it, though, as 802 kilojoules as a product, you can write different factors to make more sense of the reaction you're looking at. So if 802 kilojoules is a product, that means for every mole of CH4 that you burn, you're going to release 802 kilojoules of energy, which is kind of cool. And we get that because it's one CH4 making 802 kilojoules. And likewise, for every 2 moles of water that you make, you're going to get 802 kilojoules out. So you can see how this can be important to chemists. All those relationships, those stoichiometric factors, where we compared reactants to reactants, reactants to products, products to reactants, etc., etc. This is one more version of this we can do now. You can have 802 kilojoules per 1 mole of methane. You can have 802 kilojoules released per 2 moles of oxygen burned. There's lots of different kind of applications for this, which makes it pretty cool. So here's an example of a kind of application of this kind of process that might be helpful to you. It says how many kilojoules of energy are released when 128.5 grams of methane, CH4, are combusted. And there's the reaction again. Methane plus 2 oxygens makes CO2 and 2 waters, and minus 802 kilojoules is the delta H value for this reaction. So what we're going to do here is we're going to turn grams of methane into moles using the molar mass. And then we're going to use the fact that for every mole of CH4 that you burn, you're going to get minus 802 kilojoules of energy out. So what that looks like, you start with the grams of methane, turn grams of methane into moles. Methane's about 16.04 grams per mole. And then methane is part of the reaction. 1 mole of methane is in your one reaction, and 1 mole of the reaction minus 802 kilojoules. So when you multiply all those things together, you get minus 6.43 times 10 to the third kilojoules of energy out. That's the energy released for burning 128.5 grams of methane. And it's a lot of energy. And that's what we use. Natural gas is what this basically is, methane. It gives off a lot of energy, keeps our houses warm, keeps our it keeps our hot water heaters going if that's what you've got. So it's a pretty cool fuel source for what it's worth. But anyway, this just shows you an example and how you can use these for your advantage. In this example, we'd like to know how many kilojoules are released when 32 grams of oxygen are combusted with methane. So this is a similar kind of problem. We're going to go grams, in this case, of oxygen to moles first, and then we'll use the conversion in the reaction to turn moles of oxygen into value of delta H. So the molar mass of oxygen is 32.00 grams per mole. So 32 grams of oxygen divided by 32.00 grams per mole is 1 mole. However, in the reaction itself, it says that there's 2 moles of oxygen burned per 802 kilojoules. Now we have 1 mole of oxygen, and there's 2 moles of oxygen for every minus 802 kilojoules. So we're going to take that 802 and divide by 2. The answer here comes out to be minus 401 kilojoules of energy. So again, grams to moles is the first part. And then 2 moles of oxygen are burned for every minus 802 kilojoules that come out, minus 401 kilojoules. Most enthalpy values, most delta H's, have a little 0 kind of next to them, or a degree symbol is a better way to think about it. And that degree symbol is standard conditions. Standard conditions means that you're at a pressure that's about an atmosphere. It's equal to a bar, and an atmosphere are almost the same thing. If you have a solution, it's 1 mole per liter. If the temperature is there, it's going to be 25 degrees Celsius most of the time. And usually the species that you're reacting with are in their standard states. So carbon standard state, the one you see most often, is graphite. Like you wouldn't use diamond because that's a lot more expensive and rare. You wouldn't use C60, stuff like that. Oxygen, you would have a gas because that's what we're used to dealing it with. We breathe it in. It wouldn't be liquid oxygen or something like that. So if you see that little degree symbol, it just means standard conditions. And these are the kind of conditions you would have under standard times. So if you did reactions, say at the North Pole where it's a lot colder, you may have different values of delta H than your delta H standard conditions number would be. Likewise, if you were on Mars or if you were in Death Valley, somewhere like that, you would have slightly different values of delta H as well. In problem set 3, there is a pretty long list of different chemicals at the back of the problem set, and there's several different columns. And the column that's important to us in problem set 3 are what's called the standard molar enthalpy of formations, delta HFs. And these are actually pretty cool. Now, how this table came to be, there's a group in the United States called the National Institute of Standards and Technology, NIST, and people sit in their offices and basements and stuff, and they figure these kind of things out all day, and they create elaborate tables of what's called a standard molar enthalpy of formation. So if you have a standard molar enthalpy of formation, that means that you're making only 1 mole of product, 1 mole of compound, and you form that compound from elements in their standard conditions. And these are the numbers that you can look up in that table. In the background of this slide, like right there, and right there, you can see some of the representative values of delta HFs, the standard molar enthalpies of formation. A lot of them are negative, but not all of them. So like C2H4 there is positive 52.3. More of them are negative than not, but there are a lot of positive ones. But you don't need to worry about that. You can look those up in the table. And again, they're in your problem set. You can also find it online. If you go to mhchem.org/thermo, you'll see the list right there. It's also in problem set 3. One thing that's not listed in the background picture, but you will see in the table, is that all the elements in their standard states will have heats of formation equal to 0. So standard states would mean graphite for carbon, but not diamond, because diamond's a lot more rare. Oxygen as a gas would be 0, but not ozone, not liquid oxygen, stuff like that. So standard elements in standard states will have delta HF values equal to 0, and that'll be important coming up. So for these next sections, if you have that table next to you, either from the problem set or from mhchem.org/thermo, might be good to go. So the question here, what would be the standard molar enthalpy of formation equation for potassium permanganate? So we don't want the value of the delta HF, we want the equation that would go along with whatever delta HF value you'd look up in the table. And again, the punchline for these kind of questions is that you can only have 1 mole of product, and all the reactants will be elements in their standard states. So this would be the heat of formation equation, the standard molar enthalpy of formation equation for potassium permanganate. Only 1 mole of product, so there's 1 KMnO4 right there. And the reactants are going to be elements in their standard states. So potassium's normal state is a solid, manganese is a solid, and oxygen is a gas. So 1 K and 1 M and 2 O2s make up 1 KMnO4. And if you look up that value in our thermodynamic table, it comes out to be minus 813.4 kilojoules per mole. So if you form KMnO4 from the elements, that's the energy you're going to get off. And it's you're getting it out because it's exothermic, all right? It's a negative number, which is kind of cool. KMnO4 makes a really nice purple solution. So in the lower right-hand picture there, KMnO4 solid is on the right, and it is kind of like a purple crystal. When you place it in water to make it KMnO4 AQ, it's a really nice purple color. It's one of my favorite solutions. It's kind of cool looking. So here's a question you might see. Which equation below defines the standard molar enthalpy of formation, i.e. delta HF, of gaseous methanol? All right. Now, methanol is CH3OH. You want to have just 1 mole of product if it's a heat of formation reaction. So notice the answer E has a 2 right there, so that means that E is not delta HF. Delta HF, only 1 mole of product. So A through D all have 1 mole of product, but not answer E. Now, the other part, in addition to 1 mole of product, is you must have reactants as elements in their standard states, and that means no compounds. So H2O is a compound. That means D is not going to happen. In C, CO is a compound. Answer C is not right. And answer A has methane, CH4, another compound. That's not an element. Answer A is not right. So what this means is that answer B, by default, has to be the right answer. So if you look at that, it has 1 mole of product, CH3OH, and all reactants are elements in their standard states. So carbon solid would be graphite. There's a total of 4 hydrogens, so that would be 2H2. But also what's really frustrating to me is that because you are limited to 1 mole of product, you have to use fractions sometimes with these. So we would have to write, even me, I would have to write 1/2 O2 because we only want 1 oxygen atom in methanol. So we have to use fractions here. So again, because you are limited by 1 mole of product, sometimes you, and me too, will have to use fractions when writing equations. And this is the only time time, I want you to use fractions when writing equations, all right? Only with heats of formation. All other examples, we'd multiply that by through to get, say, answer E. But for heats of formation, it's always 1 mole of product. Elements must be reactants in their standard states. I got to deal with it. You got to have fractions.